and King's College by King's College in London. So go ahead. Eugene, I think you are muted.
All right, can you?
Okay. Yeah.
Sorry about that.
Okay.
I'm still not well versed with technology, as it turns out. So, well, thanks for inviting me to this very interesting conference, and I am really enjoying it so far. And the conference organizers asked me to talk about gravitational wave from boson star mergers using numerical relativity. So I know what I thought I took the liberty to change the title to like gravitational wave of exotic compact objects for reasons that you will see in the next slide. So this is work done with Thomas Helfer, who is a postdoc at Johns Hopkins, Katie Clough, who just become a lecturer at Queen Mary, my PhD student Bo Zhuanzhe, and people in Cambridge, Uli Sperhacker, Mira Radia, and Robin Croft, and of course, with our code GR Chombo, which we are very proud of. So, what are exotic compact objects, right, or boson stars? They are basically self-gravitating coherent fundamental boson fields. And there are many names for these things. You can call it a boson star, oscillatons, there's a typo, solitonic stars, and various permutations of these names. And nobody really agrees of the nomenclature. So some people call boson star will mean something, and boson star will mean other thing. But everybody agrees on that these are compact objects and these are exotic. So I'm just going to call them exotic compact objects. And the idea is that you have some potential, and this field can self-gravitate, so they can form some configuration, add gravity to it. They'll just like support itself through some mechanism of pressure. They are not really isotropic pressure, but they can support themselves, and they can support themselves in a very, very compact way. So, and for example, the example that I show you is a real scalar field basically oscillating up and down. And this oscillation generates some gradients that gives you pressure support to prevent gravitational collapse. And hence you can form this quasi-stable state. They are very, very stable, can last for longer than the age of the universe. And they can be, although I say exotic compact objects, they can be fairly diffuse. So they can be used to model, say, dark matter halos of the galaxy cluster size. Or can they be they can be highly compact. So they could be just neutron star compact, for example. And as we all know, when something is very high compact and they're moving very fast and you throw them next to another matter distribution, you can generate lots of gravitational waves in collisions and ring formation. So this is why it's an interesting object to see. And also this is why studying exotic compact objects or boson stars has blossomed in the community after the discovery of gravitational waves 6 years ago now. I feel old now. Yeah. So, oops, let's see. Right. So there's some basic features of echoes, right, or exotic compact objects, and they are, these basic features. These basic. I'm trying to get rid of this screen because this thing is hide non-view. This thing is actually blocking my own view. Let's see. All right. Okay. Well, this is one. So there are basic features of echoes. So first thing is that they are bosonic. So if you like, since they are bosons, as we discussed earlier, large occupation numbers means that we can describe them as coherent classical fields. Though they could be scalars, which is what we normally use, or it could be vectors like Procast stars, and people are starting to study those things. And there are kind of two broad classes of these things. They're the charge. If you have a global U1 charge, for example, or they can be uncharged, like just a real scalar field. And if they are charged, they can be a little bit more compact, a little bit more stable because the charge provides some extra stability to the thing. But sort of like the things that I'm going to say is broadly applicable to both of them. They don't differ that much. They are technically different to model, but their basic physics is more or less the same. So for example, for the simplest possible model you can think about, which is just some m square phi square model, which is, if you like, one of the most common models that we use. You can kind of estimate the mass of an echo or exotic compact object to be just kind of like m squared divided by little m Planck squared divided by little m. So if you like, the smaller the mass of the potential or the field, the bigger, the more massive object you can make. In general, they depend on higher order interactions, so let's say 5-4 terms or 5-6 terms, but the value more or less remains the same. They don't differ that much. So I use the word compact. So what do you mean by compact? So you can define like some like rough value of compactness by just taking gm, which is m is the mass of the object, divided by r, which is radius of the object. So if you like, if it's a black hole, then we know that black hole has structural radius of 2gm over r. So if the object is as compact as a black hole, then the compactness will be like 0.5. To just give you an idea, like the compactness of a neutron star is about 0.2, 0.1, depending on the models of the neutron stars. So, so roughly speaking, like the echo can be any compactness, right? They can be 0, so they are very, very diffuse, or they can be highly compact, or at least theoretically, we think that they can be like 0.5. But if you try to actually construct these models, you will find that most models become unstable around 0.1 to 0.3. And it's a kind of an open question whether or not we can construct like models with potential or giving them spin, or just actually write down and try to solve it and show that they are stable. Can we get to actually 0.5? My own suspicion is that probably not, but it's really an open question. We don't really know what the answer to this question. So what do you mean by stability? So one way to think about, you can always write down a configuration that has a very high compactness, but if you perturb it, if it's too high, they'll just collapse and form a black hole, right? So roughly, here's an example to show you how it works. Like, so again, use the simplest model, which is the m² phi square. And it turns out that for a model like this, it's a single parameter model. So this line here is the solution. So y-axis is the mass of the object, and c is the compactness. So if you just crank up the compactness, eventually you find that at some critical point, increasing the compactness will decrease the mass or decrease the energy of the system. So it becomes unstable, if you like. So this point here is the critical point. So for like some m² phi square potential, like m² phi square real scalar boson star or echoes, you find that the highest compactness it can go to is about 0.14. If you start adding like charges to the system, adding interactions, you can push it higher, but the values are roughly, you know, there's a maximum value of this compactness. And this is actually a important point that we'll come back to a little bit later. Right, so, but of course you can have much more complicated models. For example, like the one that Marsha was talking about, if you have an axion, then you have an additional parameter, which is the axion decay constant. So now your phase diagram, if you like, become a little bit more complicated. So here R1 is when you can form a stable axion star, and R2 is when you become collapse into a black hole, and R3 is unstable, but it will disperse. It will not form a star or a black hole. And then you can do a bunch of simulation to show that this is how the phase diagram of the system works. But the point is not to know all these models. The point is that if you throw more features into the system, then it just gets more and more complicated. Right. So why do we care, right? Why should we care? And other than the fact that they can give us a chance to write papers and get promotion and stuff, they are like good dark matter candidates, right? So if ultralight scalars or axions are now one of the more popular models of dark matter. So if dark matter is ultralight scalars, then in principle they will form these compact objects. So we should try to look for them. So give us like like one of those things that you can write in your grant proposal, which is like we're using LIGO to detect dark matter. So it is an attractive idea, but also people are interested in this kind of non-black hole, non-neutron star object. Is that we want to ask ourselves, do we actually see black holes, or do we actually see some other crazy stuff? So can they mimic the behavior of a black hole, for example? So I think the way that I like the way that Katie Clough, who's now at Queen Mary, sort of like describe why we care. It's like they're in general practice problems. Like we are physicists. We are trying to understand new physics. We do not know what the new physics is. So this boson star is like sort of a good way for us to get our hands dirty to try to understand how to deal with non-black hole physics. So we are all in training, if you like. We are training to be Jedi. Like when eventually LIGO or ultra high frequency detectors see something crazy, we are all ready to deal with it. And she's right, because trying to deal with, as you will say, right, trying to understand boson star raise a lot of those problems that we don't encounter when we just decide to do just black holes. I mean, it turns out that it's actually much more complicated to do than black holes, because they're just more stuff, more moving parts. So, okay, so what kind of gravitational wave signatures do we have for boson stars? Roughly, there are two classes. The first one is that, you have two boson stars, they orbit each other, they inspiral, they collapse just like two black holes or two neutron stars. And you kind of get these coherent signatures of individual events, right? So this is the famous GW 150914 result. We get a strain versus time diagram. But I think for this community, for the ultra high frequency gravitational wave community, we are more interested in like stochastic signatures of many accumulated events. So if you like, we are interested, so the way that normally we plot it is not in terms of a strain versus time diagram, but more like an energy density of a stochastic gravitational wave versus frequency. So this is just a thing that I took out of a review paper, which I completely forgot to cite. So I apologize for that. So as you would see, a lot of work for boson star has been always focused on trying to get the top one, because the community is driven by looking for these objects in direct detection, LIGO, LISA, and I should say LVK actually. So so looking for them in a strain versus time diagram, and there's not much work done to actually try to understand what their stochastic background is. So I will talk a little bit about that a bit later. Okay, so another thing that we should talk about, but I will not talk about, is that there are also gravitational wave from like black hole interactions with ambient boson fields, and I think Marsha has given us a really good overview of that, so I won't talk about this. So, all right, so we have this boson star, we have these things here, and what kind of frequency range can we expect? So it turns out that if you have a binary, instead of a binary black hole merger, you have binary like boson star merger. Roughly speaking, the ECO of this object is modified by the compactness. So instead of 3GM divided by, instead of 6GM divided by 3GM divided by C. So the peak frequency is roughly then just inverse of R cubed. And then you can just plug all the numbers in, and I took this from the ultra high frequency gravitational wave working paper, so I cannot be wrong. If I'm wrong, then you all guys are wrong. Then you get this number, right? So you get this, if you fix the compactness of the object, then it's sort of inverse to the mass of the object times 10 to the 6 hertz. So you can just plug in the numbers and see what kind of constraint that you have. Remember that roughly speaking, the mass of the echo is just m Planck squared over the little m, the mass of the boson. Then for ultra high frequency gravitational wave is 10 to the 6. Then the mass of this object has to be 10 to the minus 3 solar mass, and I plug in the numbers and I get constraints like so you can look for this axions or this ultra light scalars or these bosons where the mass is more than 10 to the minus 6 eV. So this is where the ultra high frequency gravitational wave will probe. This is the range that you should be looking at. And it's kind of like open range, right? We don't have much constraints on this range, so it's good. So so now we have talked about boson stars. What are the main difference between boson star or echoes versus the standard black hole and neutron star mergers? So personally, I think the most important thing is that black hole and neutron star are actually very rigid objects. So we always say that black hole is the object with the highest rigidity. And what we mean by that is that if I take a black hole and I give it a kick, it will shake a little bit, but it will ring down rapidly. It will just, he wants to go back to spherical shape as soon as it can, like with the very, very, very short half-life. So it's very rigid. You give it a kick, it just, you release all the gravitational wave and it becomes a black hole again, but become a spherical black hole again. Well, boson stars are actually squishy, right? So you can they're like more like Play-Doh, right? So if you squish them a little bit, they would deform, and then, but they will want to go back to the spherical shape, but they don't go back to the spherical shape as fast as either black hole or neutron stars. So they're very squishy, which means that if you think about it, if you throw two of this together, if you throw a black hole together, I mean, it might be a little bit surprising to you, but if you throw objects of a black hole compactness together, you might think that, oh, this is the most gravitational wave you can get because black hole has strong gravity, right? Well, you'll be wrong actually, because if you actually throw two boson stars together, which is high compactness, you actually can get a lot more gravitational wave, and we actually show that numerically in this paper. And the reason is just because they are more squishy, so there are just more ways to generate quadrupole moments. So it's not obvious that colliding black hole always gives you the most gravitational waves. And of course, the next thing is that since they're squishy, they will have a very different quasi-normal mode spectra. So by looking for this particular spectra, we can hope to see, the difference, one of the ways for us to tell whether or not we are seeing a black hole merger or a neutron or a boson star merger. And the third thing is, they don't have really surface. So if you like, they are because they are scalar fields, they're fundamental scalar fields. They sort of like at some effective radius, the scalar field is just asymptote to infinity. But how fast the asymptote to infinity depends on the Yukawa interaction of this field. So it depends on the model. They could take a long time or long distance or short distance. And the upshot is that it means that if you have two black holes that are far away, they just interact gravitationally. But if you have boson stars that are far away, they can actually interact not just gravitationally, but also through some scalar force mediator. And that gives us additional handles on this object. And finally, sometimes, the boson stars are really not fluid. So we can't really model them as fluid. They're not like neutron star or star. They're supported by like scalar gradient pressure, which is actually non-isotropic. So this is sort of like basic difference between boson star and black hole and neutron stars. And let's come back to the idea of instability, high compactness. And so one of the things that can be like a unique signature for this boson star is the following, right? So we remember that if they are high compactness, they are not stable. So if you have two of them that is very, very high compactness and that get close to each other. So this is a numerical simulation. You can see the boson star like falling into each other. At some point, the perturbation of one boson star will perturb the other and it will collapse into a black hole. So they will then form a black hole before they actually collapse. So if you just like extrapolate this to inspiral. So if they're far away, they're in spiral, they might look they would in spiral together, and then because they have additional scalar force mediator, the change in the frequency of this in spiral will be different from that of the black hole. But at some point, they'll reach some critical distance when the perturbation was going to affect each other and they're going to both collapse into a black hole. And suddenly they become just two black holes merging. So you can, maybe one possible signature is to look for the rate of change of the frequency of the in spiral and see if you can see a sharp spike, because this collapse is very, very quick. So this is one possible unique signature that we can look for. So, all right, all good, right? These are all great stuff, right? So what I'm going to talk next is this is actually a hard problem. There are a lot of problems. How long do I have at this moment? How much time do I have?
You have 7 minutes.
7 minutes? Okay, I got to be quick then. So there are physics problem and there are technical challenges, right? So we have formation history and technical challenges. And what I'm going to talk about is just briefly the two problems that we are trying to attack. So the first problem is like if you want to look for coherent gravitational wave, we need to understand initial conditions. And if you want to look for stochastic gravitational wave, you need to understand formation history and populations. So gravitational wave from ECO Inspirals, as we want to talk about. So this is just a simulation of our thing. Two boson stars just basically in spiral. It take a long time, so I'm just going to skip right through. So there are some early attempts to try to understand this. Like Valenzuela and his group done a lot of work on this, and people have done like colliding echo and neutron stars. It turns out that it's actually much more difficult than black hole for the reason that I just explained, right? They are just much more complicated objects. I'm going to skip this. And one thing that people use is to try to set up initial condition is just to linearly superpose two independent solutions, and people use that. Like in the last few years, this is what people do. And what this means is that you take two boson star solution and you want to construct the metric, you just add them up and subtract this normalization factor. And you hope that if they're far away, they don't actually affect each other. So this is actually quite a good approximation. It turns out that if you just make some general simple estimate, it turns out that even though they're quite far away, the volume element of one boson star affected by the gravitational field of the other boson star scales like square root of the distance. So the effect of gravity actually goes down very, very, very slowly because it goes at square root of r. And then if you just do, even though they're very, very far away, the echo is actually puffed up by 1% initially. And you might think, okay, I can live with 1% initial change in the volume. But as you will see, right? So it turns out that because your central density has an additional central density of your object is so high, even a small change in the volume will change the energy density by a lot. You can see that the rho profile changes and you can see that the radius actually changed by 10%, and the central density changed by 100%, right? So what you have put in that you think is two very happy boson stars is actually two very, very excited boson stars, and you have really very little control with that. So what we came up with is some quick and dirty fix. And this is we call it the Thomas fix, because Thomas Helfer, who was my PhD student at that time, figured this out, and now we have came out with a lot more detailed examination of this fix. Now, instead of replacing it with this delta ij, we can replace it with the central metric, or the metric term of the center of the other star. And it turns out if you do this very simple fix, you actually fix like a lot of problems. It doesn't fix all the problem, and it fixes a lot of problems. And here's the plot that shows how it does that. So this is the distance. As they go far away, you can see that this unfixed, the black line, which is unfixed, and the red dot, which is fixed, the unfixed is just diverged by a lot. So if you just add this in, you would fix basically a lot of your problems. So this is actually like the cheap. I think Uli just say this, that this is the most bang for the buck fix that he ever seen in his like 20-year career in numerical relativity. So this is great. Right, so, and given using this, this is actually just hot off the press. We now can simulate inspiral boson star up to 30 plus orbits. And this, nobody actually managed to do this before. Like people can get maybe 2 orbits or 3 orbits, but we can get now 30 orbits. And this is because that the initial conditions are just much more controlled. And hopefully these are just hot off the press. We have to do a lot of tests to make sure that this is what we are expecting, but we are getting there. So I'm going to, because in the interest of time, I'm going to split whether or not ECOs have stable spin. I'm going to go to the stochastic gravitational wave section, which is what people are interested in. So just like black holes and compact binaries, if we expect there will be a population of this echo flying around in the universe, then we should expect there will be some stochastic background, right? So great. But the problem is that we do not know how to calculate this population. I mean, we just no idea, right? So the good news is that, I mean, the good news in terms of a lot of work to do is that the large meshed range for ECO models, you can construct, like you can just write down like whatever mass for your ECO models. Then it means that you can generate, like in principle, generate lots of gravitational waves at very, very different frequencies. That's very different from the standard compact binaries like neutrons and neutron stars and black holes. We sort of have a very limited range, right? You cannot have neutron star of 100 solar mass, for example, or neutron star of like 0.001 solar mass, while you can have echo of like 0.01 solar mass or echoes of 100 solar masses, for example. So you have a lot more freedom. So including at high frequency ranges, which is what we are interested in. So how much work have we done? Very little work, right? So and I'll tell you why. Like, so if you, for example, this paper by Juna, which is actually very interesting, is that if you assume that echo tracks star formation, then this is kind of like the background that you would get. And also, you can also assume that maybe at the end of inflation, you can generate all these echoes like oscillons in Evangelist talk just now. Then maybe this will give you some background gravitational wave from the early universe. But what about the present universe? What about them as equivalent to the black hole or compact binaries? We can form relativistic echoes from collapse of cosmological perturbation, and it turns out that you can make them like today, not maybe today, maybe like like redshift of 5 or redshift of 6. And this is our simulation that you do. You start with some random perturbations, you turn the clock, you simulate it, and eventually some of them will, I mean, this is very, very messy, but some of them will collapse and form a highly excited boson star or the compact objects. And from there, you can make inference of what you can calculate. So the problem is that these are incredibly expensive simulations to do, right? So what we can do is maybe form 1 or 2.
2 minutes.
Okay, yeah, I'm almost done. I've got like 2 more pages basically. So you can make them, but you can make like 1 or 2 of them because they are very expensive simulation. You're solving full GR equations in a very big box. So there's like, for the moment, there's no large scale simulation or relativistic formation. They're just way too expensive. What we can do, at least for us, when we did this paper, is to try to infer populations from just doing some estimates. So what we can do is that we can simulate the overdensity fields. So this is something that we can do fairly cheaply, just looking at the overdensities. And by using our simulations to figure out how much overdensity you need to make a boson star or make a black hole. Remember, you can always collapse into a black hole instead of a boson star that will make primordial black hole people very happy. instead of a boson star. So you can just then make an estimate about what is the population like. So for, I don't remember exactly what the mass scale of this problem is, but for certain mass scale, you can make a population that will fit right into the LIGO band. And this is if you like the boson star, and then you have another population of black holes, right? So this is another way of us, maybe if you see some primordial black hole population in this mass range, and you see some boson star population in this mass range, just give you an idea that maybe the primordial black holes actually comes from collapse of some boson field. And you can change this frequency by just changing the mass of your boson, like I said just now. But this is really like early work. I mean, there's so much work left to be done, and just, it's kind of an open field right now. I think people should get into this. So finally, here's my summary. So echoes are much more complicated and richer objects than black holes, because they have plenty of hair. They have scalar fields, so it makes them much harder to simulate. There's a lot of technical problems to be overcome. We are making good progress in understanding echo mergers. We are not quite there yet. There is a lot of technical issues to solve, but I think we are making really good progress. But for the study of population or formation of echoes to get stochastic gravitational wave, this is actually quite, it's quite sparse. There's a lot of work to be done here. So I think that's the end of my talk. Thank you very much.
Thank you, Eugene. So we have Juan already. Go.
Hi, Eugene, nice talk. I enjoyed it very much.
Hi, Juan, nice seeing you.
Nice to see you. So there was a claim that GW 190521 came from the head-on collision of two boson stars. But from your talk, I had the impression that that could not be, right? Because the way those black holes finally merged and ringed down would show that they were not boson stars. So they must have collapsed already as they approach each other into two black holes.
I see. I know what you're saying. So that object, that event that you said is used to describe basically everything in the world and everything.
Yeah, we have very few oscillations, right?
The reason you can is because the ring down and the merger phase is it's so loud, right? So what you don't get to see what the inspiral is. So what you get is basically a ginormous spike. So you can hide a lot of your unknown physics.
No, but you see the ring down. You see the ring down. You see the normal nodes. It's
yeah, but
you see very few oscillations of the inspiral, but you do see the merger and ring down. And well, even though from there they claim it's a boson star, but from your talk I did use this.
I mean, we actually have a paper that we claim that it may be cosmic collapse of a cosmic ring actually.
Okay.
No, it's the thing that the statistics allow you to hide a lot of stuff in that, and I'm not being like it is true, right? It can be a boson star. It doesn't rule it out, but I think that being able to fit it doesn't mean that it is what it is. Like, for example, as I said, we can also fit it with a collapse of a cosmic ring. So it unless we get like a much more high definition signal, I think it's going to be quite hard to see these objects.
I agree. Thank you, Eugene. All
right, Nukta, and then another question, and I think we need to move on.
Thank you, great talk. So I had a question.
I can't hear you.
Oh, can you hear me now?
Yeah, I can hear you now. Thank you.
Okay, yeah. So I had a question about the squishiness you mentioned. So what could be the possible reason? Is it that the fluctuation in the energy, like the potential, or?
I think it's just that they are not as compact. So the squishiness come from the fact they are fundamental scalar fields, right? So unlike neutron star, which have neutron star are not fundamental scalar field. They are made out of neutrons, and then you have some sort of a fluid description for it. So they have in addition to the energy density, they have like between the particles, they have interactions. While for scalar fields, they are just fundamental fields and they are bosons, and bosons are like don't care about, there's no Pauli exclusion principle to keep them away from each other. You can have a lot of bosons in one place or no bosons in one place. So they become squishy in that sense that you can deform them fairly easily by just applying a tidal force. There's nothing to stop them from just having a if another way of saying that you can calculate what their sound speed is, and the sound speed is not as high as the black hole. Like they are just, you kick a boson star, they will do this. In fact, one thing I skipped is that maybe there's an example to show you is so here's what happen when you kick two boson stars together. So this is when you take two boson stars and very high, quite compact boson star, and you slam them together with an impact parameter. Our goal is to form some sort of a spinning boson star, and what you get is this boson star that is doing this shape, right? With like they do this. So they are black, and they do this for a long time, right? Unlike black hole, they will do, and then they will go back to the spherical with symmetric. But a boson star will just do this for a long time, and in fact, it's such a long time that you can actually get post-merger gravitational wave, which you can look for. So one of the way to look for post-merger boson star is to look for this. I don't want to use the word echoes because that's such a loaded word, but this oscillation post-merger, which in a way I think is actually quite novel, right? I mean, usually when you collide neutron star or black holes, they don't have long post-merger gravitational wave for boson star that you have.
Okay, thank you.
Okay, Fernando, very quickly. And I think we can continue the discussion also during the coffee break, right, Francesco?
Just a quick question. A great talk, Eugene, as always, very inspiring. You mentioned about the potential. Essentially, you said that in many you can get essentially the same effect for many potentials. But in your calculations, you use only the m square phi square, or
we use various one. I mean, for this one, we actually use a full axion potential with a cosine potential. So like for, I mean, like this one we use m square phi square potential, but for this guy where we can get like this high frequency, like this very long orbit, we actually use a charge. So it's m square phi square, but with a complex scalar field that with a U1 symmetry. So this gives us extra stability to be able to make this out multiple orbits. We are trying right now to do this with real scalar field, but it's much harder because without the charge, without the global charge, it makes them a little bit less stable to work with.
right? Okay, thank you.
All right, I think we are done with questions. So
thank you. I'll stop sharing.
Yeah, stop recording.